Hello, everyone, and welcome to Handmade Hero. We would like today, well, what is our W drive here? It is already. We would like to today fix, we sort of have a bit of an issue, which is that we would like to fix what happens in our code, in our lighting. We'd like to fix what happens when we have lights that overlap probe locations. And so we've gotten to the point where the lighting is actually working really well. I rather like it. I think it's really cool. But the problem that we now have to face is that we've got this sort of bad scenario that occurs right where things are in the world when lights overlap the actual probe locations where we're taking our light samples. And to show you how that is kind of bad, you can see that as this sort of moves around, as the glove kind of moves around, you can see that the light, off center. So for example, look at the wall, right? The lighting on the wall responds almost, it's like perfect, right? It looks like it's tracking really well. It looks like it should, and the light plays across the wall very satisfying, right? And that sort of it's really cool, right? It's complete global illumination. We even have this in a more dramatic sense. If you want me to give a more dramatic example of what happens here, in the entity gen, if I turn off, we've got this thing that sort of like adds lights to rooms. It'll probably have a little more logic to it in the future. Right now, just kind of like add some lights to rooms. If we don't have any lights in rooms, you can kind of see what I mean more dramatically. So you can see that the global illumination responds like basically perfectly. I mean, it really looks great. But the actual light directly around, like the immediate location of the light source, seems to like be very intermittent, right? Like as it kind of goes around, you see this, like sometimes it's really bright, sometimes it's not there at all. Like what's going on? Like why is it so bad right around the light? Well, some of it probably has to do with the fact that it's never going to be exact, right? Oh, sorry. I forgot about that. Apologies. That was funny. I always forget to change it. I'm not sure why. I can see it. Like I can literally look and see it. I just forget. Anyway. So yeah, point being, it looks really good on everywhere except right where the light is. And actually, although some of that may be sampling, meaning there's going to be some the lighting is never perfect, and especially when we're on the CPU side, we can only cast so many rays. If we move this over the GPU, we may be able to cast a lot more, and so it might improve there. But if you look at how good the global illumination is, it really looks fantastic, except for right over the light itself, where you can see that sometimes it looks good, and sometimes it's almost like it's not even there, right? Like you can see here. And you might ask, what's going on there? Well, the actual problem there, we have basically a thing we don't really know how to handle, or maybe we shouldn't say that we don't know how to handle, we at least do not handle. If we go to full cast, we have this this part of the function here. You can see where we look to see whether we're inside a particular light probe, whether a particular light probe is inside of an actual piece of geometry, and if it is, it does not do the casting, right? So what ends up happening here, if you look at debug draw, so I'm not sure how we can really show this without the screen being filled with garbage, but I'm going to fill the screen with garbage anyway, and I guess we'll just have to live with that. So basically, like, here is, what's happening. So what you can see here is the glove like in this case, for example, and you know what? Maybe let me kind of get at a level where you can sort of see it a little bit better. Not sure how to do this exactly, but maybe something like in here. So if you look at what happens when the glove itself is overlapping, right? The probe gets eclipsed, right? What's happening when the probe gets eclipsed is that we no longer can really take lighting samples that will hit this thing correctly, right? The light itself doesn't. What we would like is for this probe to represent the fact that there's a light right here that's supposed to be shining out in all these directions, and so there really shouldn't be what you see here, which is that the sampling from the light is totally unable to actually gather. And I'm not sure, like, let me look a little closer. It's kind of hard to see exactly from that angle, but maybe from this angle you can see it a little bit better. So what you can see here, right, is like the light probe itself is unfortunately, inside. So it can't really do much with respect to that light, and now we are missing the fact that there should be a really bright light here. Now, if we just moved the glove up so that, or made the light smaller so that it wasn't so large, then it wouldn't encompass and we would get totally different results. And that's a huge problem because we don't want that's not at all what we want, right? We don't want to have suddenly whenever lights encompass sample error points, we don't want them to suddenly get dimmer. And you can see what's happening here. Now, all of, we get a proper, like, this looks more like what it should look like. There's light in this locus. It's exactly what we would expect. Why is that happening? Well, it's happening because now you can see none of these probes are actually inside the light volume. All of the probes are themselves kind of outside, right, of the light volume. So they all sample, at least reasonably well, that there is a light there, and they represent it with lighting, which is exactly what you would expect. So you can see why this is important to fix, because, we really don't want it looking like that splotchy kind of, it's here sometimes and it's gone other times kind of effect. We do not want this, right? The question is, what do we do to fix it? My assumption is that since we already do a pass to bucket all of these pieces, right? Like, you can even see that it's happening here. If you look, when this light crosses a boundary, so is that going to do it? I'm trying to see. Yeah, like, there's a boundary right there. You can see that we already split the light right into two pieces, because what we're doing is we're creating a spatial hierarchy that, it's like a grid. It's not really a hierarchy. It's just a spatial grid that we can cast through. And we already subdivide lights so that they fit inside these cells, which means we're already doing a pass on the, on all the geometry to put it into this spatial partition to begin with. And so the question is, could we potentially just at that point take these lights and rasterize them into the light probes to solve this problem? That's one thing we could do. That's like an analytical approach where we basically say, okay, let's, when we're doing our insertions of the light into the spatial partition, we could also do an insertion of the light into the light probe grid where we add the light into those probes that it overlaps. And The problem with that approach is it's a little bit confusing how you actually do it. You have to come up with an analytical answer, right? Where we're just going to basically take well, I guess we could sample it as well. I don't know. It's really hard to say. But we would need some way of basically saying, look, here is for this light probe region, here is how much of the box is overlapping. And we need to translate that into a lighting amount. And the problem is, like, that light probe can still hit. So I'm just not sure. And there are other ways, like we could introduce noise in terms of the sampling location. So meaning like the placement inside of a particular cell that we're going to sample the lighting from could itself also be jittered. There's yet another solution to this problem. I don't know if this is a great idea. So an alternative solution to this problem is to say that we simply don't allow this case to occur. And I know that's a weird thing to say, but actually it's not all that difficult. If you imagined taking the light probes and requiring that the light probes themselves be effectively floored to the location of the floor and ceiling, and then you clipped light sources so that they were never quite that high, that would be the end of it, right? So, in other words, let's suppose that we forced all light probes temporarily to be, like, lower, right? So they're, like, down closer to the floor. And, these maybe a little higher, but they're pretty high already. Like, we wouldn't really care if that was how high they were. That's actually fine. It's not an issue. So, we could do something like that where the lights where the lights are not allowed to really be in those locations. They're effectively carved out of overlapping. There are some issues with this. Like, the problem is that, you want probes to be roughly where the things are that you're lighting. And so you're going to have this problem of the light will always appear to sort of be coming from the wrong place. You know what I mean? So that's a little bit meh. I really just don't know. I wish I had something better to suggest, but to be completely honest, I really just don't. I feel like I should be able to think of something, but nothing really comes to mind that's particularly logical. Randomized sampling locations does seem somewhat like a thing. By the way, I like the spec lighting, by the way. You can kind of see the specular lighting happening there. It shouldn't be happening on grass because at some point we need to send down some material parameters. But I really like the specular lighting as a tool for later, like where in the future we could play with that to have shinier or duller surfaces. So I'm a fan of the specular the potential for the specular lighting, even though right now we're not really using it, right? Like, you can see why it might be fun to have that kind of a wash, right? You can see like it kind of plays across the floor. And it's not going to be great because our sampling is not dense enough. It's not going to be as good as like if we did some kind of screen space stuff, right? But I think it does add a little bit of character, and it's free in our current scheme, basically. It's just one extra texture sample at the time that we're doing the lighting, because we already computed all of the coordinates and everything, and it's just like, well, that's not true. We did, I guess you wouldn't need the reflection vector, so it's a little more expensive than that, but it's on the GPU side and it's pretty cheap. So since we already have the map lying around, I do think like getting that in there, so you can see that, right? Hopefully. I feel like that's pretty good. But yeah, like so I'm pretty happy with like everything in the lighting except this part of it, because I don't really know the right way to solve that. And I don't know that unless we jitter, like jittering our sampling locations is the only thing I can think of that would cleanly solve the problem, but it's going to inject a lot of noise, I would think, right? Because if we randomly sample our locations, then we could just make it so that when you hit a light source from the inside, that counts or something, right? And then I think it just kind of works. I mean, maybe I'm wrong about that and that doesn't work either, but it seems like that would probably work. Don't quote me on that, but I feel like that probably works. So yeah. I mean, I guess one thing I probably should do is to try jittering the sampling locations, because like if that doesn't add an appreciable amount of noise, then I suppose that would probably be the right approach, because it also improves the sampling more generally. So like, you probably get softer fall off. You'd get maybe less of this sort of thing happening here. God, this lighting looks so freaking good. Like, remember, there's only one light in the scene, and it's completely dynamic, and it looks so good. It's just so good. Anyway. So maybe we could try jittering the sampling locations inside the cell. The reason I feel like that's maybe a little bit tough is just because I don't know how to sample the cell. I guess you just sample, well, I don't know. Let's just try throwing white noise into the sampling location, and we'll see what happens. I think what we're doing right now... So we have some problems we'd have to solve too. So like if you look at what we're doing right now, we basically just, if you are inside an occluder, we don't cast. If we are, so we do allow you to cast from inside the light source. I think you just never hit that light source, which is the problem. So I guess another thing we could do is have it so that you can hit the thing that you are inside of. So we could try that. We could try that. So I believe the problem that we have is that if you look at how this box, this is a intersection code for the box, and effectively what it's doing is it's computing the hit, and I believe, yeah, like you can see, so the way this works is it's computing the minimum and maximum hit on the box. So my assumption is the problem here is that it will pick the, yeah, okay. So if you look at how this code works, I realize it's a little bit hard to read because, again, this has been optimized. So it's, one of the problems when you really try to turn the optimization crank on anything is that it becomes harder to read the code. It's why we don't, that's why I say, like, there's optimization and there's, like, non-pessimization. And you always want to, do the non-pessimization, right? You always want to write code simply, clearly, and do the minimum amount of work. But actual optimization, where you start turning the crank and like rearranging things and eliminating terms and all this other stuff where you're actually getting more aggressive, that does make it harder to read. So this is, going to be harder to understand because we've done that on this code, right? So if you look at what's happening here, you can see that it's trying to take the t values along the ray. So how far you've gone along the ray. And it's trying to take whatever the minimum and maximum of those would be for the intersections with each of these boxes. So you can see here how this proceeds. It's doing that on each axis, x, y, and z. And then it's taking and it's figuring out what the maximum hit would be on x, y, or z, and the minimum hit would be on x, y, or z. And then this t-valid check is saying if the minimum is greater than 0, and then the min and the max, they have to be spread. I believe this term right here is the thing that would prevent us from casting from the inside, right? Because this is saying that the minimum hit has to be forward from the origin. Yeah? Meaning the origin of the ray we're casting out, we have to have gone in the direction of the ray. We cannot go backwards along the ray. If the minimum hit would have been, then we're inside. Now, that means we're effectively already testing for whether we're inside or not. And so what maybe is the correct thing to do here is to change this to say, let's just remember that we were and deal with it later. Maybe that's the start to making this work well. And again, I'm saying maybe, right? I don't know, but maybe that's what we should be doing. So if that was what we're going to do, then we wouldn't bother with this, right? So this would just simply not occur. So we're not going to do that. And instead, in fact, I guess we're just going to clip all the way down to here, right? So we're always going to cast from inside of everything. And if we run that code, then the first problem that we're going to get, and you can see it already, right, is that now the thing that this was designed to prevent, which is that the interior probes, like probes in here, are now able to see lighting from the other side, right? Now, you can't really see it that well, and maybe, looking at it, maybe that's just, you could just leave it that way. Maybe that's not a huge deal. I don't know. We'd have to put lights back in the world. I'd probably turn lights back on to make that decision. But now we're able to hit those when we're casting, right? But we also now are, so they're able to cast outward, but we haven't actually done anything about the problem of this light, because the light, it's never going to gather from something that it cast inside of, because this code is going to prevent it. Okay. So now we have this problem of, well, we would like to sample this hit, this tmin hit, right? We'd like to do that, and the problem is now we just need to track this. So the first thing we might say is, well, okay, so the tmin and tmax have to go in the right order. So maybe we're talking about something like this, and this is like t inside. Yeah? You know what I mean? And to be honest, I don't know about this part here. But basically, I think what we want is something more like this. You know what I'm saying? So our test would be, the tmin has to be less than the tmax, because if it's not, then it's not a valid intersection anyway, right? The tmax has to be greater than 0, because otherwise the hit is completely behind us. Completely. We're not inside it, it's just behind us in the opposite ray direction. And we want to make sure that it is the closer hit. So if we already had a hit that was closer than this one, right, we would want to use this one as our hit. And so this now allows us to cast from inside, I would argue. This term is not used yet, and will create problems for us, I would argue. I mean, I don't know that, but I believe it will. So now we should be able to cast inside, and the light itself, we should be able to hit, but we got one more problem, which is that the normal will be pointing in the wrong direction, and I don't actually know what happens now with the light in that regard. So whether or not this is actually testing what I want to test, I'm not sure. But I think it would be. I'm not entirely sure. So let's take a look. So you can see, like, it's not doing what I want. Like, it is actually doing the cast, but the casts, it's treating this as if it was an occluder. Like, do you see how they all went dark? So something about the way that is working is broken, and I'm not sure exactly what's going on. I assume this code is working, but I guess I don't actually know. What I should probably test first is, well, I guess I know it must be working, right? Because if it wasn't working and you weren't hitting the light, it wouldn't go dark. It would just hit something, right? So I believe this code must be working. But the question is, why is it black? It should be picking up the emission, I would think, but it doesn't appear to. So I'm not sure what's going on there. Why would that be? Because this hit emission, it should have picked up leaf is emission. I would have thought. Interesting. So let's take a look. No, I'm not assuming this is not used at the moment. I'm saving that for later. So what I'm assuming though is if you hit an emitter, I would have assumed that it doesn't matter what direction the normal is facing. I would have thought that would have provided emission to you. Because something hit will be true, I would think. I guess I don't actually know what is this about. Oh, I know. This is for selecting the normal. Yeah. So anyway, if something was hit, we come down in here and we use this code. We really should rewrite this code probably to be just ray bundles now, because I think that would be the more efficient way to do it. But you know, it is what it is for now. Anyway, so we come down here and we try to figure out like where we hit this thing and blah blah blah. We do like, you know, we do the occlusion and we do all this stuff. But I thought like this computes the normal, right? And all that garbage. Then when we come down here, my assumption was that we don't use any of that because it's an emitter. So my assumption would be that it would just use the emission level, right? Like the emission level is here. We do ray weight times transmission level. Times the hit ref color. Which, yeah, I mean, it's just the color of the light, right? So I'm pretty sure this is fine. Like right? Because the emission level is going to override the reflective light here. It's emission. So that should just work, I thought. But I'm obviously wrong, and I'm not sure why I am wrong. Although I guess I can think of one. It's a bit of a long shot, but I can think of one way this could be wrong off the top of my head, which is that this this H comp this nonsense here might have something to do with it, right? So basically the H comp is doing a min-pos EPU 16. Okay. If something in here were to be negative, right, that would be the thing that ruins it for you, right? So in here, I guess what you would have to say is like, if we're going to we've picked a mask already at this point, so you would need something like that. You would need to say, okay, the minimum T value, we're now gonna like clamp it so that it can't go below 0. Yeah. That would allow it to still get picked, right? Okay. And so I guess at least I'm slightly gratified that, hey, that does appear to sort of solve the problem. Although, I mean, it doesn't solve our lighting problem, but it solves the problem of the light not getting found when it overlaps the probes. Like, now you can see that clearly worked, right? Like, it's much brighter around the probe now. It's also kind of wrong because, like I said before, now what will have the opposite problem, which is that if the glove is not overlapping anything, it will be much less bright than if it is, because as soon as it overlaps a probe, everything that comes out of that probe hits that light. And then as soon as it comes out of that, it's not, right? So this is why I was saying there's no good solution. If this I thought was going to work just doing that, I would have said, oh, that's the solution. So you can see why I think there's a problem with it, and it looks like that in practice. This is why I say we might have to jitter the sampling locations, but I think it'll add too much noise. If we jitter the sampling locations, then you wouldn't get that because you would only see sometimes from inside the light, right? Okay, so the question, though, is also how much work would we have to do with T inside to make this thing work okay? Surprisingly, we're not really getting any light bleed, which is not what I would have initially expected. What I would like to do is add lights back to the system to see to what extent that's actually true and to what extent that's the artifact of that there's so few lights that it's hard to get light bleed because you don't have all that many lights to actually cause it, right? But to my surprise, like, it just looks fine. So I guess using T inside doesn't actually prove necessary somehow, which is super bizarre to me, and I have no explanation for that. I guess it's just because since we're using the actual occlusion normal test when we sample lighting, because the normal is pointing away from us, we assume it can't reflect light back, so it just works. I don't know, man. That's not true. I don't know why that was ever there. And so here we're going to say, like, all right. So we stuck a big old comment in there just trying to say what we're currently thinking, because that's not intuitive to me. And while I can come up with an explanation for it, it's a bit surprising. It probably warrants further study. As you can see now, we don't have the problem we had anymore, but we have the opposite problem, which is that the light appears to be extremely bright, but then it's overly bright because it's when it eclipses it, 100% of the light samples now have that light. As soon as it uneclipses it, 100% of them don't. And by the way, I find this to be actually quite educational. Again, just as someone who doesn't work with lighting very often, the most I've ever worked on lighting is what you're seeing here, right? Like Handmade Hero is by far the most I've ever done with lighting. That's why I'm constantly surprised. I'm like, wow, this looks amazing, because I didn't know that we would get it to look this good, right? And it's still CPU side. Like, we're not even using the GPU for this lighting, which is insane. So yeah, it's pretty cool. Anyway, but if you look at what's going on here, it's basically very educational from the sampling standpoint again, because remember, what we've seen so far is that we get square interpolation artifacts when we have a discontinuity in the function that is represented at the sample points, right? And anywhere that that's not true, it's very smooth. And this is precisely that discontinuity. So when we are in between probes, we have a smooth function being sampled by those lights, those cast rays. It's a smooth. Everywhere the percentage of rays that hits that light source is correctly proportional to the distance from the light source, as it should be. But as soon as we eclipse one of these with the light, then just that probe has 100% of its rays accounted for, and all the other probes around it are fall-off based. And lo and behold, the sampling that we see now shows a very prominent square artifact. Is that why? Again, not a lighting expert, so I'm not prepared to say, but it's just very interesting to note that every time we have a known discontinuity in our system, it seems like we see it in the interpolation very clearly. You know what I'm saying? So anyway, looking awesome, and this is actually better than I was expecting. So I guess what I'll say is maybe we start trying to jitter the sampling locations and see what that does. Again, I think it's a great thing. It's a great approach because it just continues like the Monte Carlo style lighting integration that we're doing, but it's just like, it's noisy, right? It's noisy. So you would expect to get exactly what I think we're going to get, which is too much additional noise. Now, because our lights kind of move horizontally mostly, there is one thing we could try, which is only doing like our light samples could jitter in X and Y, but not really in Z. Might help reduce the noise because there's one less dimension. I don't necessarily know that that's a very compelling conclusion, but Now, it costs us something to do this. The cost is this, right? Like the sort of way that we're doing our initial stepping. This stepping initial P, that has to get computed every time because ray origin single will change every time. So effectively, like ray origin single, which is used down here, right? So yeah, it's just got to get propagated down, and I don't know how much that's going to cost us. Probably not all that much, but it's worth noting it's not free. So ray origin single is actually getting computed outside, and if we're sort of saying we're just not probably going to do like the handling and full cast anymore, full cast starts to look pretty pointless, right? So it's entirely possible that what we actually want to do now is just get rid of full cast entirely. Because if you imagine what this is going to look like, we don't have, do we have a retired directory? We don't. Do we? Yeah, we do. So like maybe what we do here is we just say, like, you know what? Full cast is going in the bucket. And maybe we leave it there. And then we're just going to weld this stuff into grid raycast and call it a day, right? So instead of it being what it was before, we're just going to say, all right, it's really just full cast. It calls it in here, and it needs these, things. So let's just make those things happen, and stop with all the fancy foot, Just stop fancy footing around this. Just stop with all the fancy footing. You know what I'm talking about. Too much fancy footing, right? So let's just weld these together, It's something we wanted to do for a while. Now is obviously our time to shine. It is our big day in the sun. Everyone knows it but us, so let's just do it and call it a day. Okay. So this stuff I saved and it's just going away. We're just not gonna do that. We've got this preamble, which we do sort of still want to do, right? Like we would like to have this raycast debugging garbage occur, and we do kind of need to remember what we were actually using as the call. But I think other than that, we don't have to care very much. So light probe P was getting passed down. So ray origin here was not doing anything. So basically, like, ray origin single was just light probe P. Spec atlas, diffuse atlas were not a thing. Tile was tile. Initial grid index was solved this way. And yeah, like, I guess that's just it. So now my argument is that now we're calling, full cast is just its own function, and we don't have a subcall to grid raycast currently, right? And off we go. I don't want the debug drawing anymore because I don't care about it, and so I'm gonna turn that off. And now I'm going to look at jittering the starting locations, which, is a little bit more in-depth, right? But it's an attempt to try and actually measure how much of the light is actually overlapping a probe instead of just assuming that the entire thing overlaps the probe. And, we're not expecting miracles from that. I don't imagine it will actually work particularly well, but we're going to do the best we can. I'm also going to make debug pick be the thing that happens here so that if we're doing this, then debug pick is a real thing. And otherwise it's not. This can sort of just go directly in line, probably. So this can probably just all be done in one step. And I don't quite see how enabled was getting set before. Did I accidentally, like, delete that, I guess? So here, this is what makes it enabled, right? If it's... This is what actually makes it be enabled, is this R equal to. So shouldn't this just set it to be that? Right? I don't know. I'm not quite clear on what's happening there. I'm not gonna lie. So I don't know about the debug cast. We should probably go make that, like, retest that. Because I don't actually know. That was just some sloppy nonsense. But I don't care right now because we're not trying to debug that. So what I would like to do now is I would like to now take the sampling location and jitter it, right? So I'd like to jitter the sampling location to see if that makes it so that this is less absurdly discontinuous. You know what I'm saying? That's cool. So I'm going to go ahead and give that a shot. And so to do the jittering of the starting location, what we would need to do is say ray origin single is going to kind of come down and not actually be determined until we pick, you know, probably the ray index. So like when we pick the ray index, like that's when we pick ray origin single. So the things that we're getting done, like it looks like that, for example, the things that we're getting done based on ray origin single have to now like occur later. And it turns out that was almost nothing. So that's fine. Although some of these values may have gotten hoisted out. So we may lose some optimization being done by the compiler there because we haven't really looked at that. We kind of hacked this code and haven't really like re-optimized it since. So, you know, take that with a grain of salt. It may not really be only one thing that's getting optimized there. But if we take this at face value, then we can, if we would like, do effectively this, which is to say we take the ray origin single X and the ray origin single Y, and we can add entropy to those probably bilaterally, right? We want to displace in either direction. And I don't know how far, like, probably the whole tile dim. So not the spatial grid, but the atlas grid. We would want to do that. Now, I'm just not even going to do that quite yet. Oops, I don't know why I didn't put an equal sign there. I'm just going to let this run at the moment, which is, it's just going to be garbage, but I just wanted to make sure that this is sort of still doing something, right? Yeah, okay. So because it's one in either direction is going to be roughly correct. It's just not quite right. So as you can see, like, hey, honestly, kind of works. I don't know if it's as good as we might want it to be, but it's pretty good, right? We still get a little bit of nastiness there, but it's quite close. And to be honest, I'm okay with the amount of noise that injected. Like, it's not that bad, in my opinion, right? Okay, so if we're only going to sample inside the tile, I don't actually remember how big these tiles are, so I don't know how close one actually is to them, but we don't care because we should have that number with the atlas grid in the first place. So inside the, like, I don't remember what the heck this is called. Update lighting, is that what it's called? So in update lighting, when we go through here, we set up this voxel dim, right, with our atlas grid. So in theory, we should be able to do like, you know, jitter radius, and that should just be whatever the cell dim is of the atlas grid. We want to do like 0.5 of that. But we probably don't really want 0.5 of that. Like, we probably want to pull it back a little bit from 0.5, but, you know, for now, let's just claim that that's what we're going to do. And so we would multiply, in this case, right, like we would multiply the x and the y jitter radius by the random sample that we get. And that would tell us how to displace the lighting samples, right? And off we go. Now, I don't know how correct that's going to be. It looks a little bit wrong, but, you know, it's hard to say because this is a very imprecise thing that we're doing here. So I don't know. And you can kind of also see, like, you see how we're getting, like, the sampling, right? Because these things can move around in here. It's going to be a little weird too, right? So you get some weirdness there. Because the lighting can now sample from, you know, from further afield. So, yeah. I don't really know where to go from here. Because this turned out more promising than I was expecting, I think, is the biggest thing. Like, the jitter did not really introduce nearly as much noise as I was expecting. I wonder if that's because I did something wrong. That could also be. If we don't let it jitter the entire volume, I'm curious what that does for our light containment. You know, so some stuff is a little weird here, right? Like, I don't really understand why we're getting this light bleed. So I think we may have to investigate this a little bit more because it doesn't quite look right. So I think the raycast is a little broken, which is fine because we just said we wanted to go make sure that the lighting, the debug cast was working. And you also see there's a little bit of there's a weird kind of like disappearing act that the light does there that doesn't quite add up for me. Like, maybe that's plausible with this scheme, but I can't quite say for sure why it would be. So I just feel like we're a little, I don't quite feel like this is quite right. You know what I'm saying? Like, it feels a little like maybe I screwed something up, and I think we want to maybe draw it just to make sure. You know what I'm saying to you? As far as we know, we are backface culling, actually, though. The occlusion, this right here, is actually what that is. But it may not be working properly, right? Although it seemed to be before we did the jitter location. So that's even more confusing, right? So it's tough to say. Okay, so like if we were to go and draw these maybe, that seems good. So let's enable grid raycast debugging and see what we can see. Like I said, we wanted to make this code work, and we don't know because we kind of just clipped it out. It may not be working now, and so yeah, we would like to. I think we would have. This is now getting over brighted. I suspect that's because we set the light to something high that we probably need to fix at some point. Anyway, so this appears to be doing what we would expect. So you can see that the sampling, so let's move this down here. So you can see that the sampling does appear, I would say. It does appear to be, roughly white noise in the, I mean, it doesn't look obviously wrong. I do think we're going to need some way of drawing, like, more concretely the starting location. So, like, we need a debug box that's, like, very specifically drawing at the starting point. So, like, this, for example, we probably I don't know. Do we still want to draw that? I don't know. But when we draw the hit here, we probably need to draw, like, where we cast from. So, we probably need to do something like this. And the color would have to indicate, like, which one it was, Why I stopped the program for that, I have no idea, because I had it all set up the way I wanted. But I guess that's just sometimes I forget that we can live edit the code in this program. Since you don't always have live code reloading in engines, sometimes it's easy to remember that it's easy to forget that you do. So, I mean, that looks correct to me. I don't really see anything particularly suspicious. If we look at the interior casting, again, looks pretty reasonable. We don't really have an X-ray mode here, but I mean, that is exactly what I would expect, probably. Although I am a little confused about I guess that, like, we should make this drawing a little more specific, because why the normal pointing up is being drawn out of here, Oh, right. Okay, so that's because we're not allowing a negative on the location where the sample should have been taken. All right, so that's probably worth fixing because so like we're doing that fix in probably the wrong place. I don't really know, but like, you know, it could be that is not actually where you want to do it. And what you would rather do is when you do the cast PS, you would do it right before that. So the T-ray dot so like right before you do the T-ray.p, that's where you would do it so that nothing else actually used that value. So it's only for the horizontal compare. So it'd be like T clamped compare. Like, you know what I'm saying to you? You know, right? Do you know? So if I change it so that the comparison is clamped, I'm sorry, it's not, it's called T-ray. So that the comparison values get clamped before we use them, but we leave the negatives in place. Is that actually going to be more what I wanted? Why do I keep yeah. I just cannot get it through my skull that we don't have to restart the program. I do not know why I have this problem. Okay. So, let's try and make this a little bit more sensible. So, I think that is technically correct now. As odd as that seems, right? Like, it's basically using the far side. So, like, if I was going along this ray, what would I have hit? I would have hit that one, right? And maybe we don't want that. Maybe we want to try and use Tmax as the ray's Tmin at that point so that we hit the side we're casting towards. Guess I don't really have a strong opinion about it. Basically, I don't really know what we want there. Yeah, I don't know. I mean, we could do it either way, and I just don't know that there's a reason to do it. I really just don't know if there's a good reason to do it that way. So yeah, honestly, the jittering looks okay. So I would say my current problem is just that it doesn't seem to behave as well as I would like. And I don't know what that's actually from, but you can see that you kind of still get that sort of, you still get a little bit of that as it moves in between areas. You get a little bit of that problem, right? So So am I doing something else wrong, or is that just as good as this scheme's going to get us? You know? And I'm not sure. What I will say is that all lights besides the glove, do look great with this scheme. So I would have no real complaints. Other than that one. Meaning, other than this, I don't think I have an issue with what's going on. But that's not... And it's not so much that because, you know, maybe there's ways we address the, you know, that being a little too square looking. Maybe that's actually something we address a different way. So it's less that and more that. Do you see that, like, that lighting intensity variation? That just looks either like a bug or a limitation of the scheme that I don't like. Right? It looks like water reflecting... Oh, you mean this? Like that? Yeah, that's the specular. So I turned that on because I thought it was interesting, and I wanted to remind us to do something with it. Probably. We don't have to, but basically in the shader, we can take samples, multiple samples. And so what I did is I took a specular sample. So if we want, we can turn it off, right? If you just want pure diffuse. So basically, like, you know, instead of that, you would get this, right? And now there's no reflectivity at all, right? So that's like a purely diffuse material. It reflects the light the same in like all directions, like literally all directions perfectly. Nothing in the real world would really be able to do that, but here in the fake world we can. And then we have this, which is the specular component, right? And this looks like this. This you can see how shiny, right? Everything looks now. And that shininess is just because we're using the reflection vector now, and we're not blurring the map. So we get something that actually is pretty cool. Like, it actually makes the floor look a little bit glossy, right? And we don't need to use that. Like, if it turns out we don't really think the effect plays well enough because, you know, it's sampled too sparsely or whatever, then we just don't use it. But it was compelling enough to me to have, like, I liked the look of it, and as, like, we should probably do something with this, right? Like, it's just kind of cool to imagine hopping up to an area and seeing this kind of, like, that kind of light bleeding out, right, is just kind of nice. And so I think we're probably going to leave it in there. And so for the moment, we just, you know, we add them together with no particular rhyme or reason. But in the future, what we can do is have a have a parameter, some kind of a vertex parameter or something that we send down, where we just say, oh yeah, like how, you know, specular versus how diffuse is this material, and it just gives us another way to, like, use the lighting to create visual interest, which is, I mean, that's what lighting is for. In the first place, is it makes things look a lot better. So, yeah, I don't have a lot to say at this point. We more or less fixed the problem that I was talking about with jittered sampling positions, but it's still not really the quality of the result. Although it doesn't have the bug from before, it does sort of have a separate bug, which is that it still doesn't quite look, you know, I wouldn't consider it production quality, right? Maybe for like a Made with Unity personal learning edition kind of a situation, that's fine. But I feel like, we're trying to do something of a higher quality level here than that. And the rest of the lighting looks 10 times better than that. So, the problem is this is going to bring us down, right? We only look as good as our worst lighting effect, right? So we kind of want to think about what can we do here to fix this problem. Now, one thing we could do is see what happens with different light sizes. And that one, so I don't know what happens, because if we enlarge the light source or shrink the light source, we might see things, changes in the artifacts that help clue us into what's going wrong. Because, right, like I don't really know yet what the problem is. So, thinking through what's going wrong here, we can do some experiments and see, like, can we gain some insight into the problem? And I have no idea if we can or not, but we're going to try. So let's suppose that the light was less big. So I shrank it. Honey, I shrank the light. That was weird. Why did it, like, disappear? That's really bizarre, isn't it, kind of? So if it's that small, is it, like, not getting picked up by anybody? Is it, like, nobody hitting it? Although that's not what's happening, because I can see it in the spec. I mean, obviously it will get dimmer because we currently don't divide by the light size, so the bigger the light, the brighter it would be, I believe. Don't quote me on that. So I'm going to increase the brightness of this light source proportional to how much I shrunk it. Of course, it's not really proportional depending on whether this is a surface area or a volume. So I think this is giving me fairly good information. Like, right at this point, the chance of you hitting the light source appears to, I guess, just be too small when the light source is small. And maybe that is what's causing this problem. Maybe. And there's a couple ways we could get around that. Like, one of the things we could do is try to target light sources. We had talked about doing that before, where we do a basically biased sampling. Right now, I wouldn't really call this unbiased, but it is in that sense. It is unbiased sampling in that sense. So basically what you can see is the brightness occurs when it is able to eclipse at least one of the samples, I assume. To be honest, I don't know. I feel this is just like kind of confusing what's going on here. Something seems up. Maybe this is fine, bug-wise, but maybe we just got a bug in here somewhere. I'm not sure, but it just seems a little odd. Like, it seems like it's still that the jittered sampling locations are not actually are like not actually jittered or something. So that's not. That's just not right. So something is off here. And I don't really understand what it is. I mean, what if the light source was huge? Right? So now this thing is giant, and I should probably change the power because it's gonna be too strong now. But what happens if it's super large? I mean, like, it totally works, right? So it seems like it's like at some point you dropping below like a sampling size or something. So let's say it's at 2 and we drop down the brightness to try to compensate for that. It would be even less. It'd be like 1.25, right? It'd be like really low. Probably even lower than that, if we're honest about it. That's still a bit too hard. Too bright, too much. But it looks like perfect, right? Like it looks just right. So yeah, like we definitely have a problem here of just the level of sampling, I guess, is just not. Right? I mean, that looks totally like what you would expect. So we really just have a problem of like if this thing is smaller than a certain size, we get this unhappy we get this like unhappy situation. I feel very confused. I don't have a plausible explanation for this at all, really. So at what point, at what like size of the light source does this start happening? I guess would be my other question. Like, what is the actual, roughly where do I get this blinky behavior occurring, and does that tell me anything about the problem? Is it like a Nyquist sort of a Nyquist limit where it's like, okay, if the light source's radius is smaller than the, like, atlas's radius, you get this problem. Because, like, now there's still not a problem. It's a bit square, so, you know, the square fall-off stuff that we talked about before, where it's like, okay, maybe we need to fix some of that stuff. I mean, mind you, the light source itself is square, so, you know, there's a little bit of that. But, so the question is, like, at that point, I don't see the bug. So, but at 5 we did, I want to say. So at 5, it's like blinky, right? Like, it looks blinky to me now. Well, I guess not really. It's a little bit blinky. So at 0.5, it's still really not that blinky. Let's try 0.4. It's pretty solid, actually. That looks blinky. Yeah, I mean, right? And so I guess it's just like, at that point, are you just seeing, like, that is stationary, right? So what you're seeing there is, like, the random numbers, period, basically, like the crappy random number series that we use, which is probably pretty bad. Just like an XOR shift or something. What you're seeing there is that whether it's grabbing inside or outside over time, I assume. That's my assumption anyway. I could just be making that up, but, right? So another question I guess I would have is, what if we stratified the sampling? I don't know. I'm curious what happens if we stratify the sampling, so I think that I'm going to do it, not because I think it will help, but because I want to know now. So right now we do a ray count of 16. And so what we could do there is just say, well, we're going to do a ray count of 16 in a 4x, so it's a 4x4 grid and only jittered inside the grid. Is this because it's so small, the probability of a sample ray intersecting the emissive source starts to become heavily affected by the random rays distribution and whether they actually hit the emissive object? I mean, yeah, that's what I'm guessing at this point, but we have not proven that, right? That's what you would expect to be true, but it doesn't necessarily mean it is true. So I'm going to see what happens if I stratify the samples, because I can, right? So we're looping over some rate. What the heck is sample dir? Is that even a thing anymore? I don't know why we have that. Nobody uses that. All right. We can also get rid of that include file, right? Where is that pound include HH sphere? Like, we don't need this anymore, right? Okay. So the lighting octahedral map dim. Has to go somewhere. I don't know where it should go. Probably not there. Where do we normally define that stuff? Ha! Yeah, not true anymore. So the rays per texel we don't really have anymore. So I think that probably has to get fixed, right? This total light sample direction count is ray count, but this is also wrong. So the total cast initial, let's just get rid of this. We're not even doing this right anymore. We should just get rid of these stats, because if we were going to gather stats, we'd have to gather completely different stats. Right, like they're just incorrect at this point. Okay. So we would want to have this stratified. I'm in the wrong file. Go. We would want to stratify this so that the proportion here is computed by something else. Now, I'm going to do this pretty sloppy to start with, because I don't care about optimizing it till I know what. I just want to see what it does. So what I'm going to do is take the ray origin single.x n.y, and I'm going to take. So let's say that the ray index, we know there's 16 rays, so let's just take, and we'll take 7 from 0 to 7 will be our x partition. I'm sorry. There's only 16, so it's 4 bits, so we only get 3, right? So what I'm going to do here is I'm just going to pull out the bits of the ray index and turn them into stratification for the sample. So basically the X will just be the bottom 2 bits and the Y will be the top 2 bits. And that'll be that. So this produces a number where we want to take the jitter radius, right? And we want to basically turn this into a bilateral. So we want to do the same thing we were doing before, where we turn this into a bilateral. But this is going to be, like, the number's going to be 0, 1, 2, 3, right? So what we actually want is we want it to go, like, -1 point, well, -1, you know, 0.125 or whatever, 0.125 or not, 0.3, -0.3, 0.31, something like this, right? So we need to multiply it by some kind of inverse first. Because if you imagine this is a, well, Ian, actually, you know what? I can do this even easier, because since we don't care about the performance of this, I can do something more straightforward. So if we just lerp between negative of the jitter radius, and positive of the jitter radius, so we're just going to, like, go in between those two extremes. Then all we have to do is turn these numbers into something that goes from 0 to 1. So we know it's 0, 1, 2, 3, so we would just multiply it by the inverse of 3, and that gives us a t-value that goes from 0 to 1. So that's an easier way to do it, and I think that's fine, but don't quote me on that. So what I'd like to do is see what happens there. Okay, so now, in theory, this is regular sampling. Let's just verify that that's true. But this should be regular sampling, and so it's very strange that that's still pulsating, right? So something weird is up. I mean, I could have just messed it up. So, you know, doesn't necessarily mean something weird is up, but... Okay. So there's our sample point. And here's our ray index. 1, 2, 3. Bap, 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 bap. Right? Kind of hard to see why we would get so much pulsating there. Is it just because of the ray directions randomly hitting the light? I guess. It does seem a bit odd that that's the case, to be honest. Not sure I can really wrap my head around it if it's not a bug. I would vote bug because that just seems totally implausible to me. I find this unlikely. So, I'm not buying it. I'm going to turn off the jitter for, you know, so the random series here is actually seeded with an offset of the sample entropy. I'm just not going to do that. So, I'm going to instead just seed it with a constant value. This will mean that now there is no noise injection at all, as far as I know, which means there should be no way to actually produce that pulsation. It should have to be constant. So yeah, so something's majorly messed up, right? Because now we're casting the same rays every frame. So there is definitely something we don't understand, right? There's some bug that we don't get, which is great because that means that we just have to find a bug, not understand some new thing about the lighting, right? But I'm pretty sure that that is what that means because I don't see, there should be no, yeah, you can even see, like there's no actual noise injection here at all. So where's it coming from? I'm interested in why that's blinking. Why would that be blinking? So that's just the hit. It's like the hit and like there's some kind of like Z fighting with the hit and the cast are in the same place. I guess. That is a complete and total mystery. I have absolutely no idea what's happening. Well, all right. I guess we now know what our project is. It's to find that bug. I do think we need to improve the rendering of this thing, because currently it sucks. Meaning the debug viz. I know what all the things are. Like, so that's saying, look, this is a sample for this light probe. It's going out that face of the octahedral map. This is the point it picked to cast out of. That's the actual ray that it selected. Here's the place it hit, and there's the normal that it then, you know, selected for that particular hit. You know, so all that's fine. You know, whatever. But we should probably make that a little bit cleaner, right? That said, it just looks completely solid. So where the heck is the noise coming from? It should be computing like more or less the exact same thing every frame. Although, to be fair, that's not really true because it is a feedback system. It does sample from the previous frame's information. So there is a little bit more to it than that. And I suppose it's possible that this is setting up some kind of like an oscillatory regime where like it's actually just sampling from itself. It gets in this cycle. I don't see how that's possible. Like I can't even make up an explanation for that though. You know what I'm saying? So I have to assume that this is a bug, that there is noise getting injected from somehow, right? But where? I just have no idea. Where would that be coming from? Is it like a weird, like uninitialized variable kind of a situation? The glove doesn't bob. I mean, you can see that it doesn't bob, right? Like, it's now settled. Like, it's not moving now. So that's very strange. I can turn off the temporal, like, there is a very small amount of just sort of ketchup blend, basically, like a Heinz ketchup blend. And we can turn that off. So it's 12 frames. So if we turned that off and we just said that the update, no, it's not 12 frames. That's wrong. It would take, so what's that? 4, 6, it's like 5 frames. It's 5 frames. So if the T update blend is just 1, then that means it will update completely on every frame. I mean, what? That's awesome. This is going to be an interesting bug, probably something to do with floating point something. I would just like to remind everyone that there is no code in the game right now intentionally to make this light blink. It is running through, as far as we know, exactly the same code path as literally all of these other light sources that are stable and lighting the world normally. There is no code at all here to do that. That's just a straight up bug that somehow was able to produce this effect. And I have literally no idea how it's doing that. That's pretty wild. Okay. So we probably, yeah, I like whoever just said about Nans. I assume this is something like that where we did some sloppy modifications here. Something is getting, basically getting nerfed by Nan just on the edge of something, I guess. All right. Well, I wasn't expecting that. That is not what I was expecting. So, yeah, I think we probably are gonna want. I have no idea what to make of that. I do, you know what? One other thing I would like to look at, because now that we're collecting information about this is kind of crazy. I would like to take a quick look and just ask, what does it look like in complete darkness? So, does the entire light strobe, or just the local, like, what's actually happening here? So it's really more or less just those light probes, it looks like. Everybody else only gets slightly brighter or dimmer. You know what I mean? But they otherwise retain their sampling fairly sanely. And in that case, where it's actually embedded, so you're not able to ever sample that light source, only the ones around it, then it does all blink. So it's only just the ones that the light is on top of. So that suggests that it's our interior casting thing presumably causing this problem, I would guess. Right? So my assumption would be that if we, like, furthermore for testing, decided to turn that off, that we would no longer have this problem, presumably. Meaning, if in here we said, yeah, the, like, T-min less than T-ray part of things, that's not, like, sufficient. You have to actually be outside. Right? Oh, still not. Okay. I do wonder if I might be just too out of food right now to tackle something like this. Because this is going to be a little nitty gritty, and I'm kind of hungry. That never goes well. Um, so I don't have any particular idea about how to approach this, to be completely honest. Turning on NaN exceptions does seem like a good idea. I would agree with that approach. But I'm also kind of confused as to what I just saw, NaNs or otherwise. That didn't seem... Oh! Although, So there is one thing I would say about that is, are those directly on the edge? Because if those are directly on the edge, then actually I do have a thought. So hold on a second. Leave that as max for now. What is the jitter radius? Okay, damn. I was gonna say, if those were actually on the atlas or the spatial grids, directly on the border, I would have said that would have possibly made some sense, but they're not, so it doesn't matter. I assume that this cannot fix it, right? Meaning, like, so this value should not affect it at all. It should blink no matter what. This is fascinating. So it's like only on some frames does being inside the light apparently work, and on other frames it doesn't. That is really weird. I'm gonna put a to-do in here, by the way. All right. I got nothing. So we should probably get snacks and turn on Nans and step through this and try to find what the heck's going on here, because I have no idea. What time is it? It's 2:20. Yeah, I mean, let's do snack. You can do some snacks. Oh, FNARP. No, this is not even running. There's no accumulating is not even ever set to anything. In fact, we don't even need this if in there at all. We could literally get rid of accumulating as a thing entirely. Frame odd does look very suspicious, although I don't think we use it anymore either. So all of that stuff is not, doesn't actually do anything. So, right. It's just, it's doing this for some numerical or uninitialized variable reason. Again, like I said, this code has been kind of like optimized a little too far, just because it's lighting. It has to be very fast because we do it so many times. Which makes it pretty easy to have problems like this that are going to be like, you know, oh, you missed a little something because you were doing this like aggressive optimization. Very likely. So, but I think like snacks, and then, you know, let's maybe turn on Nans, or, you know, try some of the things to sort of shake out and see if we can see something a little bit, you know, more something pronounced that will kind of fall out. I don't know. Again, I can't really even guess what it would be, though, is the thing. So it's a bit weird, but, you know, we'll just say, okay, you know, something's up, so whatever, whatevs. Yeah. All right, so snack time. I'm going to grab a snack, and then we'll take a look. All right, we're back. We're back. And we have snacks. Really, that's all that required is snacks. You can debug anything if you have snacks. That was not added this stream. That was in there the whole time. It was previously part of T-valid, which was anded in, but I just moved it down, right? Right? If the ray can be negative, the ray is never negative. The ray is only positive. You can have gone backwards, and the T-min will be negative because you start out inside. So T-min can be negative, but the ray is always pointing forwards for purposes of the analysis, right? The change from throb to blink was because I took out the temporal smoothing. There's some temporal smoothing in there to reduce noise. You can... I don't know how well you could see this, actually. Let me try and show you. So, if you look, probably that's not the best. So if you look at the worlds with the lighting turned back on, well, is it just me, or is the lighting, why is the lighting so stable? We've done something really busted. That's the lighting with no smoothing right now? How is that possible? Oh, duh. Sorry. We turned off the noise. Because we were testing. So, yeah. Sorry, I can't do this, I can't do that demo without turning back on the noise. So let me turn back on the noise so you can see. So in this clause right here, if I let the actual random samples be random, then you will see the noise that I saw. It's like, what's going on? And it's because, yeah. So, it's kind of hard to see. Probably especially on stream, but you can sort of see, hopefully, how, like, you get a little bit of noise, right? And that's just because we're not taking enough samples to really capture all of the lighting. So, you know, as you randomly perturb them, you get a little bit, right? You get a little bit of noise. It's not much, but there is noise, right? Yes, it's the blinking. The flashing, right? The flashing in here. The flickering. Not the blinking of this other... This, we don't know what that is. That's what we have to solve. So you could leave it like this if you want to, but it just doesn't look very good, right? Like, it would be kind of annoying if the game just looked like that all the time, that little flickering, and so you get rid of it one of two ways. Either you do a better sampling scheme, which maybe we should do, right? Blue noise would have less of a problem. Some kind of stable sampling would not have this problem, but then you get other artifacts. Like when lights move around, you would get other artifacts, right? So, you know, you have to figure out what you're trying to optimize for. But anyway, you could leave it like that. Another thing you can do is change your sampling. And finally, yet another thing to do is smooth it over time a little bit. So that noise, effectively what you're doing in that case is sort of averaging over time so that you effectively have more samples, right? Because if you only take 16 samples out of every texel per frame, and that's not enough, if you average over 4 frames, now you're effectively taking 64 samples, which, right, it gets better. So that's why we have the temporal, like, that's why we, like, blend over time there. And, you know, it introduces a little bit of lag in the lighting, but otherwise you don't really notice, and it looks, and the flickering goes away, right? So that's why we do that. We've turned it off now because it's much easier to see this blinking behavior is literally an on-off. With the temporal smoothing, it looks like a smooth curve because it's on and it like goes up and it goes down. It's like, right, it's like pulse code modulation. So we have it turned off right now. And that's why when we're not debugging, we turn it on, is because we don't want that flickering, right? Yeah, and exactly, yes. The temporal averaging is what makes the blink turn into a throb, because it's basically doing an interpolation between full bright and zero bright that creates a curve, like a little, like, a wave, right? It's turning a square wave into something smoother by using linear interpolation, right? So it turns into something more like a triangle wave. And because it's diffusive, it's even less like a triangle wave. It's probably more like a sine wave almost, So, but all that works fine. None of that is really implicated here. That's exactly what it should have done, so that's like great. So really the only thing we're trying to figure out is why is it blinking in the first place, because we don't really understand. And so and furthermore, why are none of the other lights blinking? And also, why does it not blink if it's larger? It only does this blinking if it is small, right? So in my recollection anyway, if we were to change the size of the glove, right? So the glove at the moment is 0.4. If we were to change the size of the glove to like 0.5, I believe it just doesn't blink anymore. Right? Right? So it's like there's definitely, and you can see that it kind of might blink if it's right at the right location. So something about it being exactly this size creates, like, whatever the situation is that we're seeing, it creates this like problem. And we'll see. Oh, if this is gameplay speed related to slowing the clock, sure, I can, yeah. So MTS Mox was asking, if we slow the time step down, does it still blink? Okay, so that means that just the slight numerical difference of the glove, right, is enough to make this happen. Whatever the this is, right? Which I mean, it could be plausible that it happens to just line up exactly. And moving the time step back up again did not, like, having the low time step allowed it to get into a state where it's now no longer doing that. Which is super weird. You have to admit that's pretty weird, right? So here's a question. Is it just Z? Like, is it just because we're not jittering in Z? Right? I don't think that's plausible, but let's find out. So, if I draw everything, like, that is suspiciously at the just there, right? Right? Rather suspicious. I say. So, I don't know. I don't really know what we want to do about that. We probably don't want a full jitter radius in Z. But I'm going to go ahead and and say, all right, what if we just took the whole situation and said we're jittering on all three axes so that you can't ever pick out that kind of a crumpus, right? What happens then? You still get a lot of just like weird, like sort of sampling. I don't know. It seems to be still way too consistent. And I'm not quite sure why. Like, it should be very consistently flickery, but it's not. Sometimes it's stronger. And I don't know why. Or I don't know Z. Get it? It's a joke. Math humor is not very good humor. As it turns out, like, why? Like, what's the deal with that? I don't get it. I don't understand why it goes in and out like that. If it's purely random, something about it must not actually be that random. Because if it was, then it shouldn't have such a pronounced difference there, should it? Seems weird to me. Right? Like that part where it just kind of it flickers out. Is that because of the Z again? Maybe? But that sure was the problem in general, though. Like, not jittering on Z was a massive mistake. Right. I think the lesson we've learned today is don't mess with Monte Carlo. You know what I'm saying? Don't mess with Monte Carlo. Monte Carlo needs to sample where it needs to sample, and don't be messing with it. But I don't think we're quite out of the woods yet. We're not quite there yet. We're close, but not quite there yet. All right. Oh, and here's some light leaking, right? So here's an example of light leaking out. Which is why I say I do think, like, you know, we might have to have that T inside. Remember I said, like, it doesn't look like we need it? But we might well need it, right? And, you know, whether we do or not depends. We haven't really looked too closely at that. But you do get that sort of light leaking happening there, which shouldn't be happening, right? But it's not the end of the world. You could ship the game like that if you needed to. But while we're in here, we might as well take a look at it, right? All right. Okay. We've had snack time. The lighting looks really good. I'm pretty happy with it, so I'm not, you know, I'm certainly not complaining. I just think maybe we could go a little further with it than we have. So I think it's possible that it could get, you know, still a bit better in a way that we would care about. So I don't think we're quite at the point of diminishing returns. We're almost there, but not quite, I don't think. I think we could still get a little bit of a bigger quality increase. Now I do think at this point what we could do, though, is say we can leave it for a while. Like, it's probably good enough now that we can make the game this way. So what we might want to do instead is say, like, look, this is fine for now, and we'll revisit it again in a couple of months. And look at a few other lighting things that are more important. For example, an exposure curve. Putting in an exposure curve would be relatively straightforward and help us out. So an exposure curve, and also a notion of, like, light brightness that allows us to do things like bloom and that sort of thing, right? So at the moment, I would say, like, probably improving the light transport. I do think there's another little bit of quality to get out of here without substantially doing much. So, you know, maybe we should do that. I don't know. But I do think we could also make the decision that this is plenty good enough for real-time global illumination. Maybe up until we want to take a final pass at it before shipping. because it certainly creates the character of the game just fine. But what we don't have is any sort of concept of how bright the light should be, or how the exposure curve should go, or like how bloom should go, right? So I don't know. So that part's harder to square. I don't know what we want to do about that more specifically. Hard to say. I do think this looks really good now, though. Like, I'm pretty happy with where this is at. And that's even a pretty small light at this point. I don't know how small these lights can get now, but that's pretty good. Like, I'm kind of surprised, honestly, of how stable that is. So that's kind of nuts that works as well as it does, with no biasing towards the light source. It's obviously not perfect, and you do get, if you get it small enough, like now, you do still have a fair bit of like intensity variation that's not great, right? Like, you know, you would like it to be a little bit better than that if it could be. But it's still kind of surprisingly good, right? And there's also no real reason we can't use just larger lights in most of these scenarios. Like, the chances that we need the light specifically to be like that small are low, because there's not a lot of situations where it's going to matter that what size the light is relative to what size the light should be. I would assume, right? So yeah, if the light, that's like a non-light source. So if the light is, I don't know what the light intensity should be, but if the light is like a larger light, like the 0.75 version, then it's pretty stable, and we probably just don't have to worry about it that much, right? Like, you know, that would just work, and be fine, right? And, you know, the main thing that, you know, maybe I don't really want to do this, but, you know, if we could have had spherical lights, that would have been nice. Because it's a little bit not as good, because some of the squareness of that, I think, is just from the fact that the thing is square. It is a square light. So a square light should probably cast a square light on the ground. You know what I mean? So I do think one of the problems we have is, like, if we really want to chase the quality, in addition to like improving that sampling potentially, the other thing I think we're going to run into pretty quickly is just the fact that we probably need to add spheres. Because without spheres, we ain't going to get, you know, we ain't going to get a radial looking light source regardless of what the sampling looks like, because it ain't radial to begin with. So, you know, I'd really rather not. It complicates things computationally. It's not the worst thing in the world, but it's not fantastic. And so, you know, it slows down the raycasting. Of course, I don't actually know how much of the cost is the raycasting and how much of the cost is the sampling. I suspect the sampling at this point is actually our biggest cost, not the ray actual marching through space doing collisions. So It's possible that we could just issue the intersection code for a sphere at the same time as we do the axis aligned bounding box, and then we just have a parameter that's like, is it a sphere or is it not? You know. Yeah, I don't know. I mean, I suppose maybe the argument here is we should test it. Because it's not that hard to add it. It's just hard to add it so that it's fast, right? Like the adding of a sphere intersection code is not particularly difficult. The determining whether we can make that run fast enough for it to not be an issue is a different matter. Since most things are AABs, you could probably also do another thing where you actually just put the spheres in some other... Like, if you know that the only things in the world that are spheres are light sources, you could just do a separate pass over those that you don't do that for, right? But then again, I suppose it depends on how many lights you have. You know, maybe you've got a lot of these. In the actual game, like, there's all these projectiles and stuff. And then you don't really want to be doing that. I wish I had something more constructive to say here, but I really don't. Maybe we just need to sleep on it. Because I think, like, eventually you're probably going to have so many of these lights flying around, like, for projectiles and crap. You're probably going to want them to be, you know, you're probably going to want them to be bucketed just like everything else, so that you're not running through giant lists of them all the time. So, you know, you would probably just need them to be in the array like everything else. What happens if we create the worst case scenario? So, like, super bright, super small. That should be, like, really noisy. Would be my guess. But I don't know. We'll find out. Surprisingly, it's, you know, it's really not that bad, but you can see the noise, right? Like, the reflective noise sort of on the periphery, right? You can see that pretty good. And the specular would be very noisy, right? Like, right? Because it's not getting filtered like the diffuse is, where it's, you know, kind of going through another another pass there, right? So I'm torn. I apologize for being indecisive here, but I really just don't know what I should do. Other than hang out with the puss. Because that's always a plus, regardless. Yeah, so... I should also mention something that's probably not obvious from what we've been doing. That I know, but maybe not everyone out there knows or hasn't thought about. So if you're wondering what normally happens in engines here, so obviously most game engines don't actually do real-time global illumination quite on this scale. And the reason for that is actually because their geometry is just a lot more complicated, right? So we happen to be dealing with a world that's like very simple. Like it's not, 100,000 polygon models moving around in like complex worlds. It's just these like, it's this like block world. So we can do like global illumination in real time, and it's not a huge deal. When you want to do that in something like, Unreal Engine or whatever, they have to use more like sparse point sampling plus these sort of like transfer functions. It's a long story, but point being, they couldn't probably be as aggressive as we're being here. It's not plausible for them because their geometry is too complicated. They have to do something simpler. But they also do something that we're not doing, and again, it makes a difference here. So one of the things that they do is they special case, well, all engines special case light sources. We don't. So in our world, there's no difference between a light source and anything else. The only difference is that a light source emits light and other things don't. That's it. But as a result of that, it means that they know that things are light sources. And so what they then do is they do things like shadow mapping or direct raycasting of just the light source to compute their lighting equation for the direct lighting. What that means is they don't care about this, what we're seeing here, right? Because they would never have this. They don't care what the direct illumination component is of the light source from the global illumination. What they're actually going to do is use the global illumination only for a secondary lighting value that is not the primary lighting value, which is computed directly, right? So we are doing something fundamentally that is not what you would normally do. And that is one of the reasons why we're having to think about this, because you normally wouldn't think about this. You would normally split, and the system that we've written would only be used for your indirect bounce. I hope that makes some sense what I'm saying. So your indirect bounce lighting would be going through a system very similar to what I've got. Just maybe a little less aggressive because you would need to be using simplified versions of your geometry or whatever. Our geometry just already happens to be simpler. But you would not be using it for the direct lighting. Because we currently are using it for the direct lighting, and maybe one could argue that we should not be doing that and we should just special case lights. Maybe. I don't know how productive that would be because we kind of have this problem of like we don't really there's no geometry for this guy, right? Like it's just two flat sprites that are sitting there in the world that happen to line up, right? So I don't know how good direct lighting is really going to look when you don't have real 3D geometry. Like I'm not even sure what you would really do. I mean, I mean, it's hard to say. Like, we could just, if we move this to the GPU, we could just actually do it that way. You could do direct casting to the light sources that are nearby. I don't know. It seems like a bridge too far, you know? It seems like a bridge too far. And so for now, the only point I'm trying to get across here is that if you look at what's going on in the system, we are kind of down to the last sort of issue, which is this: how do we deal with the direct lighting around a moving bright light source, which is where we're going to have the most, trouble capturing the behavior. The reason that we're in that position is because we're doing things a little weird, right? If that makes sense. MTS mocks because they do shadow maps from the light sources. Right, so typically what you would do is you enumerate your light sources. So you say that each region that you're going to render in, right? Each region you're going to render in has some maximum number of lights that it can have. So let's say each one can have 8 lights, 16 lights, whatever it is. You then render 16 shadow maps from the light source, the light sources. And they would probably have to be cube maps, right, or whatever. You have to actually you render shadow maps for the directions of the light, and then you compute the direct lighting using that. So the direct shadow is captured by a shadow map, or on newer RTX cards, it might just be an actual raycast because that's more accurate than a shadow map. So you just do that. And then your indirect lighting contribution, that comes from a system like this. I think Unreal Engine 5 calls it Lumen or something. I don't remember what random names they give to these things. But basically, your indirect lighting comes from a thing. And usually, much like ours, it's temporally anti-aliased pretty heavily. Whereas your direct lighting usually actually isn't. Your direct lighting is usually a shadow map that's actually fairly accurate to that frame. There's typically not a huge amount of lag to that, but there could be, right? So. All right. FNARP said, crazy idea. Since all your surfaces are XY, XZ, YZ planes, could you look at a circle around a projection of the light source onto the surface rather than spherical intersection? I don't think I know what you're actually suggesting concretely there. The reason that spherical intersection is a problem for us is not because it would be difficult to do. It's just because when you are trying to cast multiple things at once in SIMD, you don't want an if statement in there. So you would end up running both intersections at the same time because you don't know what type of thing is the thing you're intersecting against, right? That's the only reason. So it just slows you down because you do a few more computations that you then blend together. So you would not save any. You would not do yourself any favors by introducing another scheme. That would just also make things worse, right? So hard to say. So I don't know. You don't have to do either all sphere lights or all A bits. You just have to accept that you're going to get a slowdown if you do spheres. Just to give you an example, right? So just to be concrete, if you look at what happens, right? We've got these leave insertion things, right? And you've got an X, Y, and a Z and there's like a min and a max. Yeah. So if you look at what happens in sine fullcast, when we loop over those, we just do the intersection against n of those boxes at once. In this case, it's 4 wide, so it's 4 boxes at once. If you wanted some of those boxes to be spheres, then what you would do is, like there is the thing called is emission, you would have another thing that's like, well, actually, probably what we do is emission would probably just be the same. So we would say all lights are spherical, all occluders are boxes, right? So this would be 0 or 1 depending on whether it's a light, and that would tell you whether it's a sphere or a cube as well. In here, this is the computation to see whether or not this thing has hit. And what we would need to do is provide another set of equations here. So, another 10 instructions or something that do the intersection with a sphere. And then we would use the emission value to select which one of the t values, the sphere computation or the AAB computation, which one we were actually going to use. You follow me? So that's how you would have to add spheres to this system, and so it just gets a lot more complicated because you're adding a lot more instructions to this loop where we're testing things, and you would rather not do that. There are other options that you can do. You could also store 2 different leaf arrays, spheres and cubes. But then you have extra overhead, right? Like that you're doing there. There's all trade-offs, right? Space naming, yeah, a small enough box gives you spherical fall off. The problem is you're very unlikely to hit it, so the sampling gets worse. So, and that we could change by targeting light sources more. So like I said, there are other ways we could try to approach this problem. But so it's really hard to say. It's really hard to say what we want to do here. I really don't know. It's at a point where it's pretty nice. It produces great looking environments. The only thing that doesn't look great is the dynamic lights, the highly dynamic lights. They actually look pretty good with respect to how they affect the environment. They just don't look particularly good where they actually are themselves. So like the actual location right around the light source doesn't look fantastic, right? And so it does kind of suggest that you would want to try and figure out how to solve that problem a little bit better separately from other things, but I don't really know how you do that. I really just don't quite know how you improve that. And furthermore, like I am sort of concerned that there are still bugs. Like if you crank the sampling density up to something that's like going to be wicked slow, right? Like that we can't use because it's way too slow. Like, all right, so let's take 256 samples per texel, right? So it's, it's crazy dense sampling. Just way, 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 way too dense. At that point, you look and you go, this is best case. This is if there's no, right, what you're looking at on the screen now is best case. So it still just doesn't look that good around the light source, right? Like, that just doesn't look that good. It's not horrible, but it's not particularly great. Now, we could, if we wanted to, we could make this light source even smaller and see what happens there. But again, right, it's just a question of, like, at some point there's that fall off and it's not going to be great. So, like, let's suppose I did do that. I made this small enough that, like, maybe now we can consider it to sort of be, you know, small enough that it should have a fairly radial fall off because it's so tiny. All right, maybe it needs to be a little smaller even than that. And, you know, like I said, we'll go out somewhere where we can really see the fall off, and then we'll try cranking the sample density, but I'm pretty sure it still just won't look very good, right? It's still like it's just not, that part is just not going to get that much better. So here we are. And I'll try cranking the sampling density up, you know, 1024. It's absurd, right? Like, it's, you know, maybe a GPU could do this. The CPU definitely won't. Not this, maybe a Threadripper. But that's about it. And so now, like, if we look and see what's on the screen, it's like, okay, I mean, it's just not. I mean, one problem here too is, like, it's just not bright enough either, and we know we can't really crank the brightness because then you get the feedback problem. So that also suggests that we have a problem with, like, how we're sampling the lights separately, because a 1.0 light gets dimmer as the size goes down. So it's like that was that divisor problem that we have. So, like, the lights should have their brightness sort of, like, accounted for in a way. I don't know. Like, in other words, it's like these values have to multiply out to 1 or something. It's not right. Like right. It's like a little weird what's going on here. I'll try cranking this brightness up, but I don't think it's going to necessarily help us here. But you see what I'm saying, right? Like, we still have issues. There's sort of a thing baked into our system in general that makes this situation not look very good, right? And it's not so much about the fact that it's not so much about the sampling. It's, like, actually just the system doesn't quite work right. Like, there's an underlying deficiency or whatever you want to call it. So, you know. Here's me letting it run for a little while. At 1024 samples, which, again, like I said, is, like, super ridiculously dense. And I mean, I'll agree that it is very, like, smooth fall off, right? Like, you don't see the squareness of the fall off at all. Like, it's perfectly radial. It's also just not very bright, right? So again, I don't know, like, I just get that twinge that, like, there's one more, like, step here that we're, like, missing. There's, like, one more thing that, like, there's like a, and again, like I said before, this is certainly because I'm just not a lighting person. So, of the things that I would know if I was like did a lot of work on lighting, I'm sure I would just kind of know, oh yeah, like you need to structure the equations thus and understand that these units should look a particular way and whatever else, right? Like all that is almost certainly something you would know if this is the kind of code you did on a daily basis, right? But I don't, so you know, it's me kind of like looking, like poking around for solutions. So yeah, like, you know, it does, oddly enough, I will say, and I guess I don't know why, it seems weird how the power is related here, and I don't really know. Kind of confused by that, to be honest. The glove freaking out on time steps like would be nice to fix at some point, right? It's just annoying. The glove code is terrible. So like if one assumes that that is what it should look like roughly, and then like you'd go ahead and change this to 1024 to get like a ton of samples, and it kind of converges to like that looks kind of right. You can see why I'm like weirded out a little, right? I guess I have a equivalent question too, which like that just looks right. So maybe, yeah. This is really tricky. The other question I have is like, okay, so suppose we go back to kind of like the crappy one that we were having a ton of problems with before, and like it's very square. Is it square at high sampling counts? Because I don't know, right? I'm kind of, I have no idea. So that's another question I would be interested to hear, because I don't know. So here we go. You know, there's the square version, right? And if I crank the sampling up of that to a high number, does it make it less square? And I have no idea. Looks like no. Maybe. I would say that, assuming that that is what it is. So like interestingly enough, like at that point it just doesn't change. So that again to me also says maybe spheres would really make a meaningful difference here. You know? Yeah, we could disable the temporal smoothing with the 1024, but I don't think it's going to make a difference. So here's turning off smoothing entirely. So this is just full noise, right? And here's turning on a lot of samples. And like, it's still square. And again, I wonder, like, is that just because the light's shape is square? If the light shape was spherical, would we not have this problem? And I don't know. So I kind of want to add a sphere in here. Because I almost wonder if is it really just because the thing is square. I don't know. And if that were the case, then it might be worth the extra computation to fix that. I don't know. So like temporal anti-aliasing turned off, so full flicker, massively overbrighted light, so you can really see you can really see what it looks like. If we wanted to do these as spheres, then this computation has to effectively take just T-min. So what we would need is like a thing here that's like T. Okay, I don't know what that is. Did the IME just turn on? Yes, it did. We are not typing Japanese now. So we would need a T-sphere value, and like I think we would have to compute those two we'd have to compute those 2 points, those 2 T's, and then we would do a select. So the actual T-min would be a select using the emission flag, where we select the emission. If it's an emitter, we do T-min sphere, otherwise T-min. And if it's if emission's off, we take the AAB one, right? So it's pretty straightforward what I'm talking about, but we have to actually do the sphere intersection computation here, and it's going to be ugly. Spheres, like, they kind of require like a divide. Although we can probably phrase it in terms of inverted D like we did here, maybe. I guess I'm not sure if I should go to the whiteboard for this. I'm not going to be able to, or I should say the lightboard. I'm not going to be able to just like miracle a sphere intersection code out of my head. That ain't going to happen. So we should probably go to the lightboard if we're going to try and do this. This is probably too late in the stream for this, but I guess we do it anyway. Hold on a second. All right. So, what are we doing? We have a ray origin, and we've got a ray direction, like so. And then we've got a sphere with a center. And we want to know these 2 points, right? So these are the 2 points that are, whatever the sphere radius is, are away from the sphere, like, center. Whatever that point is. Maybe I'll just call that point P, because that's like the location of the thing. And we've got the the radius value for the sphere, and we want to know, like, if we have hit this thing. And if so, where? So the ray origin here, I guess we'll call this R. We can't call. I can't call that R. So let's call this. This is the light probe location. So normally I call it L. Maybe we'll just call it the atlas location. So A. So where we're casting from, and we can call the direction here D. That seems fair. So we know that we have the equation for this ray is pretty straightforward, right? The equation for the ray is just a function of the t value along the ray, and it's just going to be like A plus t times d, right? Pretty straightforward. And the equation for the things on the circle is, I guess, well, I shouldn't say circle. The things on the sphere is going to be pretty much the same, right? Like, it's just going to be saying that anywhere in space, like a sphere is just the saying anywhere in space that you are, right? We are going to have the equation be x squared plus y squared plus z squared, right? I guess I should probably say that I would like these things to be sort of centered, probably around the sphere to get rid of the p value, because we would like these would normally have the center subtracted out of them. I don't really feel like writing it quite all out that way. So we would like to maybe say that this here is the origin, let's say. So, we'll just say this is what we're looking around, and this a value we can trivially just subtract ahead of time to put it into the same space as the sphere, but, we can mess with the equations however we want later. So we know that this length, so x squared plus y squared plus z squared square rooted, that's the distance. We know that that distance always has to be, right, equal to, well, I guess I don't really know why I bothered square rooting it ahead of time, but whatever. So that distance has to be whatever our radius value is, right? So the distance from the center, just the length of that vector, has to be equal to r. And we could say this in an easier way here, right, by also just saying, like, x squared plus y squared plus z squared minus r, right, would have to be equal to 0. So we can write that kind of in a various numbers of ways, right? But the point is, we have our ray, and we want to know if we have an equation for the places that hit the sphere. We want to solve for t because we know everything else, right? So what we want to do is plug this point in as the x, y, z coordinates of our equation here. Yeah. That's like all we're actually doing. So in theory, the only thing we actually need out of this is to say, look, if we assumed we pre-transformed it so everything's around the center of the sphere, then so we got rid of the value p, which is great because now I can use p to actually talk about the point along the line. So everything's about the center of the sphere. We know we have a radius value that's the value at which we would be on the surface of the sphere. And so if we think about the point a plus td, so if our point along the ray is going to be equal to a plus td, then really all we're talking about with this equation is that the length of p minus r has to be equal to 0, or the length of p has to be equal to r. That's when you're on the surface, right? So what we're saying is that the length of a plus td minus r has to equal 0. And if we actually multiply this out, we can presumably get to the fact that I'm terrible at math notwithstanding, and I probably make some mistakes in here somewhere, we will probably get something under a square root and a plus or minus sign, which is why there will be 2 of them, and so on and so forth, right? So if we take a look at doing that, we would just say, well, how do we get the length of a plus td? Well, like we just said, that would be a plus or minus, right? And our minus r equals 0. So expanding out this length, well, the length of something is just the square root of each of the components squared. So it would literally be exactly this. It would be, so I guess you end up in a kind of slightly nasty situation that you would like to avoid here, which is the time. Trying to think if I wrote this in the most expedient way or not. But anyway, if you look at what these values are actually going to be, it would be ax plus t dx, right, squared. And you would then just do that for the other 2 terms as well. So the actual thing we care about is this ax plus t dx squared term, which if we multiply out is what? It's like ax plus t dx times ax plus t dx is just going to be distributive rule ax squared, right, plus 2t ax dx, right, because everything's positive in here. There's no negatives, plus t squared dx squared. Do I have that right? So effectively, yeah, we would end up with this is our term here. I suppose we don't have to care about this root. I don't know why. Like I said, I don't know why I put that in there to begin with, because you could have just not done that and left the r on the other side and squared them. So it would just be an r squared here, right? And you would just have this terms. So why I didn't do that to begin with, I don't know. It's because, like I said, I'm bad at math. So anyway, if we want to solve this actual equation, we would end up with these terms, right? So these are constants. The ax squareds are, and the ay squareds, the az squareds, those are all constant. So they're just added up, right? We would just have an ax squared plus a bx plus a ay squared plus an az squared. We would just add those up, and then those would just be in there. And we don't care about them from then on, right? These we actually do care about because they have t in them, right? But if you look at how this is structured, again, these are constants, like dx is a constant, right? So if we want to just imply, let's get this out here. So if we want to just skip all of the nonsense and go straight to the quadratic equation, we actually just can, because we can see we've got it right here, right? We've got a t squared term with dx squared as the coefficient, right? We've got a t term here with 2ax dx as the coefficient. There's the t, right? Here's the t squared. Here's the t. And then we have ax squared as the constant term that doesn't have a t value. Now, if we had multiplied this out the whole way, so that we had each one of these terms, nothing would change except for the fact that we'd now have one of each of these. So rather than just dx squared, we would have had like, dx squared plus dy squared plus dz squared times t squared, right? So my assumption is we literally just compute these values for the sphere, right? And they're not quite computable ahead of time because remember, we have to, A has to be put, A and D are like based on the ray. So we can't just like pre-compute them or something, which is kind of annoying. I mean, that seems pretty straightforward, but then now I'm just wondering, is there a smarter way to do this? Because there's really not much you can pre-compute in this case. Yeah. Like, that just seems like a lot of work. Maybe some of these terms, like, cancel out a little bit, but I don't really see what I've done stupid there. I'm going to try it one more time, and we'll look it up after, just to see what the smartest thing is. But I don't quite see where I went wrong there, and that does seem kind of expensive, more expensive than I think it should be. So that may just be me not having done 3D math in years. The only time I do 3D math these days is on Handmade here. Well, that's not entirely true. Occasionally I have to hack something, and like the other day I was writing scripts in SketchUp and Blender to do some stuff for Art Pipeline, so I guess I still do 3D math occasionally, but not the nitty-gritty of it like I used to. So, there's that. But I'm not sure any other way to phrase this problem, right? The point is, at some point you're going to get down to the origin of the ray plus the ray direction times some value you wanted to produce as your t value. You're going to take this and you're going to say that the length of this should be equal to the radius of the sphere. You could square both sides, right, and say that, like, the length of this squared equals r squared. So you can remove a root term trivially from it, like we did before. But again, I'm not sure that we really care, because we're going to be rooting things either way because of the quadratic nature of solving a sphere, right? So we can only get rid of one of those. We're not going to get rid of both of them, right? So anyway, if we imagined this a plus td in here, again, I don't see a lot of wiggle room there. I mean, it's going to be root squared equals r squared of, it's just going to be ax plus t times dx squared dot dot dot. And I don't see how you get around that. So at that point, you're just, the square and the root cancel each other out. So your dx squared equals r squared. And you're solving this equation of, it seems simple enough that even I couldn't screw it up, right? I mean, you're going to square this term. You're going to have one of those for each of your components, and you're going to subtract the r squared over to the other side. This will eventually be And so you're, like we said before, you're going to end up with ax squared plus bx squared plus cx squared minus r squared is your c, right? That's going to be your in your quadratic equation. I need a new marker. This thing is so dull. You're going to end up with this as your c term. Your a term is going to be the t squareds. So it's going to be just t squared with dx squared plus dy squared plus dz squared. And then your t term is going to be the interior term. So it's going to be ax dx plus ay dy plus, right? So, I don't know. Again, very rusty at this sort of stuff, so take it with a grain of salt. That might have sucked. That's just like, trying to sum it up 15 years ago brain. It's a simple problem, but, I probably missed some stuff. But that's basically it. Yeah, we do unfortunately need to know the coordinates, because if we don't know the coordinates of the intersection of the sphere, then we wouldn't know whether we hit the sphere or something else, right? Because if you just find out if you've hit the sphere, then you wouldn't actually know if there was some other intersection that was closer than the sphere. So, so it's pretty simple, but I just am kind of worried about the cost. Amusingly, we've already done it on Handmade Hero, and I don't know whether we did it well, but we already did it for Handmade Ray, for those of you who watched that, right? In here somewhere, we have a thing to raycast against the sphere, right? Here it is. And here's the code that we wrote for it. So, as I predicted, past me did the same thing as current me. We subtracted the sphere's origin from the ray origin, which gives us a sphere relative ray. We took the inner product of the ray direction and itself, which is just the length of it, right? And hey, guess what? That's exactly what I just said it would be. It's dx squared plus dy squared plus dz squared, right? That's what the inner product is. I mean, yeah, it's the same thing I just wrote on the board, right? It's the same thing I just wrote on the board, and then here's the quadratic equation, right? The root term is b times b minus 4ac. I mean, what do you want, right? What do you want? I mean, it's not that bad. Right? I mean, I wouldn't necessarily cry about it, but I mean, it ain't cheap. It doubles the cost of the raycast for sure, of the ray walk for sure. So and right, I mean, you're gonna use you're gonna use the square root instruction for this. It's gonna be like 6 cycles or something. Probably overlaps well because it's probably on like the divider or whatever. I don't know. Where is it? Let's find out. I love how freaky the like super bright lights look. I'm gonna try it as the last thing we do today. It'll probably suck, but it's fine. I just want to test it anyway. So if we go in here to, I've loaded the entirely wrong thing. If we go in here to a web browser and we type in uops.info and I open up the table and I ask it for, I don't know why these are checked because I don't have one of those. If I were to ask where the square root instruction was, what would you tell me? So, no, apparently it is not on the divider. Oh, and that's much faster than I thought it was. I thought it would have been more expensive than 3 cycles. All right. I mean, if it only costs 3 cycles. So divide is way more expensive. Is it not? No, it's not. All right, so basically the only divide that's still slow is integer divide. I mean, 3 cycles is still really freaking slow for compared to anything else. But that's yeah. That's all right. Caveat emperor, as they say. This is somewhat concerning. So it still is only on one divider, right? You can see that it's only on port 0 here. So, you know, the multiplies are dual ported. So, you know, the latency is pretty wicked. So there's that. Like you do have to have a bunch of this stuff in flight to get the 3. But so yeah, I mean, I don't know. It's not that bad. It's not that bad. All right. Well, so I mean, here's the code. And oops, didn't mean to actually. So we've already written it, and we know it at least somewhat works. So really, the main problem here is just us welding this thing into the code as it stands. So we want to compute this with exactly what we would expect. So we turn the ray origin into the, let's say the box min is going to hold the value for the sphere, the center of the sphere. I'm just saying that arbitrarily because I can. We then compute the A, B, and C values. The ray direction is not an issue, right? Because the ray has already been normalized. So, like, A is just 1. Right? Because that's not even the inverse ray direction. That's just the actual ray direction. Right. So we don't need A. A can go away. We do need B because we have no idea like what this value is relative to the ray direction. Like we have no idea, right? So we do need that. And this is like not known until after we do, yeah, I mean, is that actually true though? I suspect it probably is. I mean, the only reason I hesitate there is because since the sphere relative origin is a subtraction, and it's a subtraction between something we don't know, which is the ray origin, with something we do know, which is the center of the sphere, in theory, you could pre-compute the part of this that was constant. My guess is there's no win, meaning you would still end up doing as much or more work if you pulled out the constant part than if you just do the subtract and then take the dot product. But I couldn't promise you that. I thought I'd mention it. Like you would actually want to like write it out and make sure you wouldn't want to do what I just did is say like, eh. So the sphere radius in this case is going to be like one of the boxmans, right? So like sphere R is, I'm sorry, one of the box maxes. Like we don't care which one. Any one will do. So, you know, that's fine. Ray direction may not be an actual thing. Yeah, it's called Ray D. It sounds like a cool guy named Ray. Like, hey man, what's up? I'm Ray D. Apparently we don't have times for constants. Apparently. So that has to happen. This is just squaring the B term and then subtracting the C term. Same rule applies. And now we're not really going to go into an if statement here, right? Because we need to actually, this we have to add. We probably don't have one of those for F32X's, so we'll have to add that. But then we get to the part where, like, we can't afford to if around this. Like, that's probably not going to happen. So, you know, we're going to have to do something here. So the mask is whether or not the root term is positive, right? Because it has to be over 0, otherwise we didn't intersect. So we would need to, like, prep the mask value for that, which sucks. And it's just going to have to be, so like, it's just going to have to be another thing that we merge, right? Like we're going to have to merge the regular mask with the sphere mask. Or knock out part of the sphere mask. It's, yeah, like, welcome to SIMD sucks. It's actually totally fine if you have, you know, a thing like a shader language that's designed for it. So. The denominator of this then produces the two t values. Why are they called TP and TN? Oh, positive and negative. That's probably what we called those. Let's claim that's what we called those. And so once we have the positive and negative terms, we don't really know which one would be which, right? Oh, well, no, we sort of do, right? Because the root term is a square root. So it's not like it can be negative, right? The negative is like baked into here. So we kind of know that it's like min and max already, right? Like this is going to be like you can't add a positive value to something and have it get smaller, can you? Oh, well, can A ever be? Yes, it can. So actually that's not true, because if the denominator is negative, it will flip. So much for that. Thought we were going to get off easy there, but we didn't. Right, you see why I'm saying like I don't think so. Oh, whoa, no. I take it back. I take it all back. It's B that I was looking at. A doesn't exist. No. So, I'm sorry. We do luck out. We totally do. Never mind. Right? We're okay. So the denominator is just 2. I think. Right? And if the denominator is just 2, then really this is just multiplying by 0.5, which means that it can't, it would never flip. Right? It would never flip. So I think we dodged a bullet there just in the nick of time. I want to say that will actually compute the minimum and maximum, because let me just make sure that's actually true. Because starting at negative b, if you subtract a positive value from it, you can only get smaller. And starting at negative b, if you add, yeah. So right? Right? That seems fine. So that's cool. That seems pretty good. This is looking better than I thought it was going to. This part is all just what we already are doing. So we're close. But we've got a little bit more work to do here. So I think we're good, right? I think we're good. If everyone is down with that. Let me see if the chat's down with that. Yeah. The chat is down with that. So that's good. So those are simplified. So let's take a look at this other stuff up here. And really this is the part that's going to be annoying, because we have to basically do a separate select, because unlike the AABBs, where this is sufficient, if it's a sphere, we need this extra mask term here. So we got like yet another and, which sucks, right? That's kind of annoying, because I don't see any way out of that. I mean, maybe what we could do is set T max to 0. I don't know. We'll cross bridges when we come to it. Let's just check out the rest of it first. So, okay. So we assume that box max x is our radius, you know. We assume that the sphere relative origin we've got is Boxman is the center of the sphere. We're taking our b value is... Oh, wow, okay. So actually these can go away, sort of, can't they? So our b value is multiplied by 2, right? You know what I'm saying? And if we just didn't do that, so let's say we chat, watch me here where I do this, because I probably should have done this on the board. I didn't. So if the b value did not have the 2 in it, right? So the 2 goes away. Then in here, normally this would produce a 4. So this would actually have a 4 in it, right? Because we used to have a 2, and 2 times 2 here would have been 4. So this would have been a 4 here. And there would also have been a 2 here, right? So there's like a 2 in there, right? That pops out. And if you look, this is factorable now. So this, because they both have a 4, is like b squared minus c. I think. The 4 can come out, because it's a product, can come out as a 2. And if it does, that means that there's a 2 here, which means that all of this disappears, because there's 2 2s on the inside, which means you can factor it out. And if you multiplied it by 0.5, then you just get nothing. Is that right? Did I do that right? Watch me, math people. So that seems good. I think we followed that through. So we're just down. Well, you know, the easiest thing to do, right off the bat, is just to add our square root, because that's kind of a no-brainer, right? So like in here where we've got our other functions, like that we actually have. So we have an approximate inverse square root. So, you know, like now we have an approximate. Now we have an actual square root. So there, square root PS done, right? So now our only problem is that we need an additional criteria for intersection here that's not actually being measured by the other case. So so this will correctly select the hit that we're doing, but we also then need to add into our mask here a sphere mask value, which itself is selected this way. And this kind of sucks, but it's going to be like this. So we've got a mask that says that this has to be true in order for this to be, in order for us to count this, right? So if this thing isn't greater than 0, then you can't process this intersection. But the reason I say this gets worse is because the sphere mask here is only allowed to operate if we are in the emission case. So the sphere mask itself has to be like an, you know what I'm trying to say, right? We need to select based on leaf emission. we need to select which one of these we're going to do. So do we have all ones anywhere? If we don't, this is a little harder. We could just invert it and use an and not. Like, and then say like, okay, so it's 0. If it's emission, it becomes this term. Right? It's not great, but it's something. And so now what we would need to do is when we build the spatial partition, I mean, in theory, that's actually running now. I mean, who the heck knows if it's right at all. We can try to cabin it off a little bit. So like, yeah. I mean, mostly, right, it's this. And you know, I got an idea. Right? So if we turn this off, we now have no spheres. Like if I take this code and I said, yeah, like don't run that, then we should just get our squareness version, right? Whereas if I turn this on, then like in theory we're doing a sphere intersection. And I don't really know that we actually are. It looks kind of broken, so I think it's probably not quite doing that, but it is actually doing something different, right? Furthermore, when we actually insert these in, we have to actually set these correctly. So at the moment, these are set wrong. So what I would propose is like, something like this. So we say, okay, if lights are spheres, then when we build the spatial partition, and we insert these things in, we have to actually take into account whether or not the thing was a light. So in here, where we get this kind of thing, and it's like, is emission, we don't want to do this anymore for spheres. So the spheres, like, that's not possible, right? And this creates a potential problem for us, which is that our actual tracing is not going to be quite right because things aren't clipped to the they're not clipped to the volume. You know what I'm saying? So this could be bad. One of the really nice things about AABs is they're clipped to the volume. The spheres cannot be clipped. You would have to add code specifically to clip them because you can't clip a sphere. If you clip a sphere to anything, it is no longer a sphere, right? It's now some section of a sphere. An AAB clipped by another AAB is always a resulting AAB. So, right? So it's like not great. It's not great. So in here we would say, okay, if lights are spheres, which sometimes they are, if this box is a light, then this stuff gets set differently. First of all, the X, Y, and Z are actually like get the center of the thing. And it's not the leaf box, it's like the box bounds. Right? It's the it's this. I don't know what clipping region is. In fact, it's not even that. It's like this. This is the insertion rect, I guess. I don't know what you want to call that. But we want to use the original. So no matter what we did when we did this whole thing, we want to just use the center of that now, right? So the X, Y, and Z's get spammed out in this dumb way. And then the dimensions of the insertion rect are what we care about here. And we only store one of them, so it's, whichever one it is, right? This is going to be a radius, so like, I assume we don't have a get radius function, do we? We do. So we just say it's going to be half, right, of the dimension of the thing, and now we've inserted them in the format that was actually supposed to be inserted for lights, right? I don't know. It doesn't look promising, but again, I think that's probably just because it's buggy, not because we have concluded that spherical light sources don't work in this system or something like that, right? So now, given the current setup as it is, I'm curious to know how squarey this looks over time. Given that maybe this is actually kind of buggy and not working properly, it's hard to say, but let's give it a test. So if we blur, I mean, it's definitely less squarey, right? It's not perfect, but it's better. Even without knowing if this is debugged yet, it's probably better if we're honest about it, right? And let me go ahead and try our little trick of, instead of 16, where is that undo happening? Oh, it's right there. Let's try and set it up to something actually significantly higher than that, and see what it looks like. So it's kind of hard to say, but yeah, like, I don't know. It's a little bit buggy because the sphere is like centered wrong. Like, this is not, I don't think this is quite right, I guess is what I would say. So a little bit wrong, but it does look a lot circular, right? So I don't know. Maybe this is something we should investigate. It seems plausible that you would actually want this, and I don't know. I'm not thrilled about it, but if that's what we've got to do, that's what we've got to do. And if we should probably go debug this code. Maybe that's what we'll do next weekend. Debug this code and see what the quality's like, because it just looks a lot better. You know what I'm saying? So, and I'm pretty sure it's not right. Like, I'm pretty sure it's still got, I'm pretty sure it's still buggy, actually. Yeah, like it's off in weird ways. So it's not quite right. So we'll have to go do some debugging, but it might be better. The only way we're gonna know is if we debug it. Just to make sure we're doing this right here. So the box min x, y, and z is the center x, y, and z. Yeah. The box max x is the radius. That's what we expected. And here, I mean, like I said, we do have the problem of this could actually be just because we're doing the cast wrong. Like I said, it's gonna hit the sphere sometimes when something else should have been hit first. And that could have really unpredictable results. So that's a huge problem, and maybe that makes this a non-starter. I don't know. But so the T min, T max getting selected. I mean, it looks fine. It's a cool little beat. I don't see a lot wrong with that. That all just looks good. I just try one thing, which is like don't break. I guess I'm not sure how you would. The way the routine is structured, I'd like to try it with letting it keep going so that you wouldn't early out on collisions. I'm wondering if we shouldn't attach this to the hero instead of the glove, since the glove sucks. And I don't have much intention of actually writing controller code in the near future. We could just say, like, yeah, I don't know what this will do, but we can do it. So this adds like a head light as well. And we could just turn off the glove light for now. So it's pretty hard to say. We're probably gonna have to put it off till next time. It's hard to say whether that really is. It might be just correct, and that's just the fact that it's not actually now. It will not do the correct first hit detection. It will hit the sphere sometimes if the sphere happened to extend into that cell, and it will record it as having hit the sphere when it really would have hit something else first. And so it'd be hard to know if that was happening or not without actually instrumenting it more, right? So it's highly likely that that could just be what's happening. What I will say is, I'm not sure it's good enough. It is better. I'm not sure it's enough better to care. Why would we be having nans, though? I don't think we are. Why would we have that? I don't think we would. Would we? Right, because so in order for this. Oh. Wait, this is so this is wrong, though. Why are we doing this? Did we cut and paste this code wrong? This is supposed to happen before the square root. This is supposed to test this thing. So I agree. I agree with you, but that's not what's supposed to be happening. So the root term is supposed to be that, right? And then we only actually, I guess we just copy pasted that. So this is supposed to have the mask, right? It's supposed to look like this. I'm glad you said that, because yeah, that's not how that's supposed to work, right? So the idea here is, yes, it's true that this produces nans, but they mask out, right? But for some reason, we were testing. I don't know why we would do that, because you can't have that occur. Like, it's never going to be negative. So that was wrong. Like, this is what I think. You know what probably the problem was? So I imagine we probably know exactly what the problem was. It's this. No, this is wrong. Wait, no, this code is wrong. It should right? Like, it should be doing the test on this. So our old handmade ray really let us down here. So I don't know what the heck was going on there. I mean, it's handmade ray, which we don't technically do. Like, it was just a time killer thing that we did. So, okay. But still, that was not how that was supposed to work. I don't know that that has anything to do with the problems we were seeing, but it might. I don't know that that really changed much, but it might have, right? Because I don't know what exactly that would have done. It depends on how the nan would have compared. Yeah, it does. It actually does look like that fixed at least some of the problem, right? So I would say, I don't know, it's still kind of squarey. Let's raise the power a little bit of it and see what that does. So it's still a bit squarey. I want to go ahead and take a long sample here. So that might, I don't know. It's hard to say. Because we're not really doing perfect sphere intersection here, right? Like, it could be that we need to actually do the sphere intersections. I mean, the sphere intersection computation is correct, but we're not properly continuing the cast to make sure that you actually hit the sphere. So there could still be some artifacts in there, but at the moment anyway, if that actually is as good as it gets, if that's not part of the bug, then that would mean that, like, the rest of the squariness is just in our actual reconstruction, right? So, you know. Let's see what happens if we unsphere. What's the difference? Like, does it look different or not? So let's switch from spheres to not spheres. What do we see? So it gets brighter, which we would expect because the volume is larger, and we don't currently divide the intensity by the volume, which we probably should. Is it more square? I mean, probably. It's not being clipped to the voxel. Why are you saying it's being clipped to the voxel? It's not being clipped to the voxel. Nothing's getting clipped to the voxel. So I don't know. It might be worth keeping. It might not be. I really couldn't say. That's a tough one. What it may mean is we have to go look at fixing our reconstruction a little bit better. And if we fix our reconstruction a little bit better, then compare the differences. Right. So, yeah, I mean, I don't know. I think we just have to probably just play with the interpolation and see. We could also try writing direct values into the, instead of doing it, seeing what the interpolation reproduces, like. But yeah, beyond that, I don't really have a lot of ideas. Beyond that, I don't think I've got any more bright ideas. So I think that's probably our next week's plan then, folks, is to take a look at that. What time is it? It's 4:30. So yeah, I mean, I think it's probably pretty good here. It would be nice to get the speed, the raycasting speed up a little bit. There's a little more of a trail there than we probably want. So, like, you know, I think we probably want to try to get this up maybe to like 20 if we could. You know, maybe to something like this. Because that's pretty locked on. Not a lot of blur there, but down by 10 was a little bit worse. So hard to say, you know? Hard to say. But it does seem like 12 out of 60 is about as good as we can do right now in terms of flicker free. Moving it to the GPU might help a lot, but it seems like we have a frame of lag there, whether we like it or not, because of the fact that the values from the last frame are used for the light samples, right? So that's a separate issue as well. Because this is without any temporal blur, and you see you still get a little, right? So. And I assume that's what that's from. I guess I don't know. You know, maybe that's not what that's from. We should probably have something that moves, like, smoothly. That's just, like, a thing. We should probably create a little entity that's just, like, a light that moves around in, like, a really, like, consistent way so that we can analyze some of this stuff a little bit better. But at the moment, anyway, I don't know. I don't know. We're very close to lighting that I would say is like, yes, ship it. But it's still just not quite there for certain cases. And I don't really know what approach I think we want. I mean, it's probably good enough as it is, but I don't know. So fixing the interpolation to be less square, definitely a thing that we would like. Whether or not that gets us all the way there, though, I don't know. And I also just don't fundamentally know whether the circles make a difference. I'm kind of guessing they sort of don't. Like, it's just, hey, it happens to be brighter, so the effect is worse because it's got more volume, but I don't know that it actually matters. So we'll see. I think that's it for today either way. Thanks everyone for joining me. I will be back here. I will be back here tomorrow, is what I will do. No, I won't. I'll be back here next weekend. I don't know. I need to stop using Firefox. Anyway, I don't know what we'll do. We'll install a new web browser is what we'll do. I'll be back here next weekend. In the meantime, I did want to mention to anyone who likes movies, Anna and I are doing a new thing on Substack that you can go to if you want to. So I thought I'd mention it. It's just because we didn't feel like we always like to discuss movies and stuff, and we didn't feel like there was a good thing for movie discussions, so we made one. It's pretty easy to get to. It's just Molly Movie Club. And so if you want to check that out, that's another thing you can check out besides Handmade Hero. If you just need more Molly Rocket stuff in your life, it's over there. I'll be back here next weekend to, I guess we just gotta have to make a judgment call. Maybe we just look at interpolation quality at that point. Because maybe that's really just what it's about. I don't know. Maybe we'll have some thoughts during the week, about what we want to do. I'm not really 100% sure. All I would say is that's where we're headed. We're almost there. It looks really good, but it might be able to look a little bit better if we change some things around, so we'll have to take a look. That's it for today, everybody. Thanks for joining me. I will catch y'all back here next weekend. Until then, have fun programming, and I'll see you on the internet. Take it easy, everybody.